we divide our programs into three areas. Local network research, which is really about how we code information and transact information in these really large systems, and guarantee that critical information gets from point A to point B. Then we're going to look at network management research, which is really about seeing how information flows over an infrastructure and governing both the resources and the policies that regulate that flow, both from and as well as from a security standpoint. And by the way, a lot it was brought up earlier that there's some new studies going, including some the newest study in CyberVision 2025. And so getting to the sort of foundations of this area, particularly in the context of things like cybersecurity, which you'll hear about from Bob Herklotz after this presentation, really require very basic foundational understanding of really what's at play here. So that's, again, what we're trying to get at. And then finally, and then we have global network research, which is if you look at the infrastructure holistically, all the heterogeneous components, how they all interact, how does all of that, what's the best way to set that infrastructure up, and what's the best way to anticipate what's going to happen with it as it evolves? And finally, foundations of information systems. So each of these, if you think about these as different time scales in an infrastructure, this final part here is once you've sort of characterized that infrastructure at each of these levels, okay, what are the properties? What are the properties of that overall system that you can expect once it's been fielded? And how do you sort of define what the metrics that define these properties are? Okay, in the context of cybersecurity, you're going to hear about things like hyperproperties. Okay, these are really critical properties for cybersecurity, and the metrics and the setting the risk in terms of how these systems behave and in things like contested environments. We want to understand how to construct those properties rigorously in terms of these other mathematical areas. So I'm going to draw you a picture. I think it's always better with a picture because what we have today is a very heterogeneous set of components in a very distributed infrastructure, which is dependent on a lot of stuff. Okay, so we depend on everything from our terrestrial networks and our optical fiber backbone networks all the way to our space networks and our forward tactical networks. And when all that stuff gets combined and we rely on it for life-critical functions, we need to understand how it's evolving because people are always adding new applications to this infrastructure. And so one of the biggest things about what we're doing in this program is that we're going to measure the system. We're not going to take it for granted. We're not going to think that it's always within its current operating mode and everything's great. Because stuff changes, and we need to understand how it changes. And like I said, I'm going to draw these into the different areas I just talked about. So local network research and systems analysis assures critical information delivery. How does it get from point A to point B? And this happens at fairly short timescales in these infrastructures. Network systems management research is really about looking at how information flows from point A to point B and how you set resource policies, how you set security policies, and how you essentially govern the system once it's in operation. And global network systems research is about predicting the performance overall. When you have this really large infrastructure, can you tell it's going to meet your mission objective? And can you set a risk or can you set a confidence on doing that? And then the last part, which brings it all together, is the foundations part. So if we look at this whole activity here, this whole right part, as sort of setting up and understanding the components of the system mathematically or statistically, then what we can do is we can represent this trade space here in all of its possibilities, and that's what the system properties are. Essentially looking over all the possibilities you could live in over here and characterizing them. And that would be things like, is this infrastructure secure? Can I tell that? By what metrics do I define that? Exactly what are the properties that define whether the system is going to be resilient to the next set of disruptions, whatever they are, or is it going to collapse? And can I predict that? Is our functionality and our mission going to degrade? And that comprises a feedback loop, which is the new this is the new thing. So I didn't just design and forget this. I designed, characterized, measured, understood what the properties are, and then essentially govern the system accordingly as it evolves. as it changes. That's a big science challenge to do that. You know, we've done this in a lot of very limited contexts. When you try to do it with these really large system architectures, putting it all together is a big challenge. Okay? Great. So I'm just going to show you very quickly what each program's goals are. I mean, if you've seen this presentation before, you can see what these goals are. You've seen this in the past. But basically, as I said, in the first part, we want to preserve critical information structure. We want to ensure network and system robustness. We want to find invariant properties for an infrastructure. This is complex networks. And we want to develop a unifying mathematical approach to characterizing that. And because we want to preserve information rather than just delivering packets, we want to quantify the likelihood of a given network management policy to support critical mission functions overall. And we want to predict and manage network and system failure comprehensively. So that's complex networks. Foundations of information system takes that farther. So what we want to do here is we want to model the entire system based on the things that we discovered from the mathematical invariants from complex networks. And we want to do this from a measurement standpoint. And so if you want to know whether your system's behaving like you expect it should, things like verification and validation happen here. But they're not the classic sort of verification against pre-existing models. They're verification against what you've measured in the system. Okay? So your system is essentially an evolving model with properties, and you like to understand what those properties are and know that as it evolves into regions that keep it within in the performance parameters the people who are operating missions on that infrastructure intended. Okay? So this is about, in the end, I say at the end of the day, this is about measurement-based verification of the system. And because we want to, and we want to do good things. We want to essentially assess dynamic, Air Force infrastructures and assess their risk of failure by understanding whether they are close to meeting the properties of success or failure or not. So there's a lot of stuff going on in this program. I'm going to step through it sequentially. Okay, and basically, we're going to start looking at local network theory. All these areas have, sort of evolved with time. So coding theory is evolving, and so that's why we kind of have it flat, because actually coding theory, the actual definition of coding theory, which I'm going to talk about, is changing, okay, how we code in these infrastructures. In network management, understanding how to sparsely or with minimal resources do these assessments online is a big deal. Doing it in a distributed fashion is a big deal. How do you make that happen? Okay. And then in the context of global network theory, we want to essentially define invariant metrics for analysis of network performance. And in that global infrastructure, we want to be able to essentially categorize where we live in a state space of options. And finally, in the information systems research, we want to know what the right state space of options to live in, what it is, where we should be living with this dynamic system so that it actually gives us the performance we expect. So again, I'm going to sort of skip through. What I'm going to do is kind of build sort of what our trade space is. So I'm going to do that, and I'm going to skip to a couple individual projects, then I'm going to sort of build a little bit more of the trade space, skip to a few individual projects. So you're going to see examples of what I'm talking about throughout. Okay, so I'm just going to illustrate pretty much everything I just said now sequentially. So in the coding context, we deal a lot with things like packets. But we don't have to deal with just packets. In the context of software, we can deal with register variables. In the context of hardware, we can deal with registers. What we're basically talking about is information units. And each of these information units live at different time scales. So this is the shortest time scale. This is where the content in an infrastructure is exchanged. And so we can code that content differently depending on what our system characteristics are. So we could code in a very deterministic infrastructure like an optical or fiber backbone network. We could code with very small, over very small finite fields that's in the context of just looking at very small packets of information. And that's good in the context of, if you have a very reliable system, you don't have to, continually question whether any information got through. This works pretty well. But when your system is much less reliable, you code more randomly. You distribute more information over a wider area because a large portion of it won't make it there. And you don't want to have to rely on your protocol to essentially continually retransmit, because in these very heterogeneous dynamic infrastructures, retransmission can actually take up most of your bandwidth in these infrastructures. And this is actually true in many contexts, including, if you think about it in a software context, including cloud computing architectures, which I'm going to talk about. So all I want to emphasize here is that there are different properties depending on the statistical class you code in and the statistical class you architect in as we go along. Up here, you're more robust. So we talked about resiliency. So if you randomly code, you're more robust to disruption. But unfortunately, you incur a penalty for that. You incur more latency, computation, and storage. So these are the kind of properties we can build just by looking at time scale and statistical class. Here we have more latency computation, we have less latency, computation, and storage at the bottom, but which means we're less robust when we have disruption, but the advantage here is that your latency is much lower. Okay, so you can get stuff through quicker. Depending on your mission, you may want to do one or the other. So I'm going to illustrate in a couple contexts how this works. So, and by the way, just as a point, what you'd like to be able to do in a heterogeneous infrastructure is live over all these classes, right? So your system right now may be in this sort of unreliable state, but you may be relying more on your core sort of fixed infrastructure later. So being able to dynamically trade over this infrastructure is important. And so to that extent, Muriel Medard at MIT is actually working on a technique that enables very robust coding by essentially sparse approximation. So we send information from point A to point B in an infrastructure. We don't know exactly what's being exchanged because that infrastructure could be highly dynamic. But using parameters like coherence in this context, we can actually adjust the rate of recovery of different classes of information. And that can be parameterized based on how the system is changing. So this allows us to put dynamics into the way we code information and code differently depending on the system parameters or the system constraints. We have another project at Cornell by Salman Evestamir, who actually won my YIP this year. He also won the NSF PCASE. And basically what he's done is actually looked at network coding, which is a very popular area, in a whole new light. So network coding traditionally assumes a fixed infrastructure and a fixed exchange of information. And it sort of behaves accordingly. What Salman does is he can actually adapt the coding structure to an evolving network. And the actual coding structure learns what the network structure is, and then algebraically comes up with the best solution for a coded set of information from point A to point B. So these are two examples of how we didn't just design and forget. Okay? We actually dynamically adapt at the coding level to what's going on in the infrastructure. So now we're going to take a look at that now at a longer time scale in the system. So at the policy time scale, we're just looking now at slightly different things. But we can look at groups of packets, subroutines, and virtual memory. Okay? But in this context, we'll look at groups of packets because it's just easier. And we can do different kinds of protocols. So we can do in an unreliable sort of tactical infrastructure, we can do flooding. We can do hybrid routing. We can do deterministic routing. Depends on, very much like we did in the coding infrastructure. And they all have their trade-offs. But the properties are more or less the same. You're more robust as you do, sort of random distribution of information to, disruptions. But the bottom line with that is that if you want to get stuff there quickly, it's not as easy. And the inverse is true on the bottom. So now we've looked at a different time scale in the network. We've looked at protocol and policy. And now we can actually see that in this context, we can change, adapt now to the properties at a longer time scale, but in terms of the policies and the protocols that we're actually using in our infrastructure. So to that extent, Andrea Goldsmith at Stanford and Janina Elder, who actually was visiting, she's a Technion, but she visits Andrea in the summers, and they have actually done this in terms of wireless distribution of information. So they sparsely sample the environment that's being, where information is being transacted. And then they can adaptively select, both in frequency and in code, the kind of channel information that tells them what the best sort of policy is for, in this case, individual user access to the wireless network. And what they've shown is that in really low dimensional form, we can actually sample this trade space and get almost the exact same performance as